All right, let's get started. Good morning, everyone. Thank you so much for taking your time to attend today's webinar. Today, we're talking about a very interesting topic. If you're a machine learning practitioner, you will know that tuning the hyperparameters of a model is hard. It requires a lot of work, and the hyperparameters has a very critical impact on the performance of the model. So I'm super glad to introduce Amok, who is an engineer on Anyscale, working on the machine learning team. And Amok is going to talk about a relatively new hyperparameter tuning algorithm called the population-based tuning PBT. So yeah, let's get started. I will share Amok's presentation.
Hi everyone, my name is Amog and I'm a software engineer at Anyscale. So I work on the team developing Ray2 and other training libraries on top of Ray. And today we will be going over population-based training, which is a strategy for hyperparameter optimization, and how we can leverage Ray2 to add population-based training to our application. So yeah, so let's get started. Population-based training with Ray2. So a little bit of overview of what the talk today is going to be. So we'll first go into the motivations for population-based training and compare it against other hyperparameter optimization strategies and understand why population-based training is the most cost-effective approach compared to other approaches that are commonly used. Then we will dive into Ray-Tune library, which is a library built on top of the Ray framework for distributed hyperparameter tuning. We will go give an overview of what Ray-Tune capabilities are and how we can easily use it to run distributed hyperparameter tuning experiments. And then finally, we'll go over some of the recent developments in population-based training that we've added to Tune over the past couple of months. So this includes functionality for reproducing population-based training schedules, as well as a synchronized implementation of PBT. And finally, we will go over a new algorithm that we recently added in Ray version 1.0.1 called population-based bandits, which combines PBT with Bayesian optimization and is actually accepted into Europe's 2020 conference. So let's get started. Let's first begin with a brief overview of hyperparameter optimization, specifically what exactly is HPO and why does it matter? So, as many of you probably know, like deep learning is experiencing a rapid growth and adoption. And this is not only happening in academia, but also in industry. So a lot of, pretty much a vast majority of applications are leveraging machine learning and specifically deep learning in some sort of capacity. And we can see here that the number of machine learning papers per year has increased significantly over the past few years. So machine learning has really become ubiquitous in many applications that we're using today. But there is one little secret about machine learning. So we're all familiar with convolutional neural networks. These are very powerful and are attributed to many of the recent advances in computer vision. So here we have one of the original CNN designs by Yann LeCun. And on the bottom, we have AlexNet, which was developed after 20 years of research. But what's interesting about recent work on deep learning is that the basic idea of convolutional neural networks have largely remained unchanged. But over the last 20 years, beside the increased availability of our computational resources, we've largely modified the shape of the neural network and the size of each layer, right? So it's the hyperparameters that can actually make a huge impact on the performance of our neural network. And so this includes like the shape of the network and the size of each layer. And over time, we've seen that many new hyperparameters that have been added to more recent networks that can be configured. And these have huge impacts in performance. Right, so we see here that models are continuously getting larger and larger, with the most recent OpenAI model containing nearly 200 billion parameters. But these models are not only larger, but they're more complex. So there's a whole new set of hyperparameters that we have to tune, which have a significant impact on our model performance. And which means that selecting the right hyperparameters is going to take a lot of time and going to consume a lot of resources. So with so many different hyperparameters that we need to search over, we need an efficient and quick method to find the most optimal configuration. So given the importance of hyperparameter optimization, what are some strategies that we can use to efficiently search over this large search space of hyperparameter configurations? So two of the most naive approaches are grid search and random search. So with both of these approaches, we simply define a search space distribution for each hyperparameter. So for grid search, for example, for each hyperparameter, we simply provide a list of values that we want to search over. And for every point in this multidimensional search space, we run a few epochs of training. And then at the end, we select the best hyperparameter configuration. So looking at this figure for grid search, we have basically 9 different points that we try out, and then 3 values for each hyperparameter. But the problem with grid search is that even though these training runs can be run in parallel, they suffer because we only search over a small search space. So once again, looking at this image for grid search, we see that despite running 9 different trials of different hyperparameter configurations, the optimal hyperparameter configuration is not actually searched over. So we need a larger search space to actually get to this optimal configuration. And as we increase the number of hyperparameters, then we have to search over a larger and larger number of different configurations. And ultimately, as we saw before, because the size of our models and the complexity of our models have increased drastically over the years, searching over a large number of hyperparameters is just simply very expensive and not feasible for a majority of people. So we can improve grid search slightly with random search, which basically means that instead of providing a list of values that we want to search over, we provide a distribution. For example, we can search over learning rate with a uniform distribution or a normal distribution, for example. So this is a little bit better than grid search because we can add some stochasticity to our search, which potentially can lead us to an optimal hyperparameter configuration. But like grid search, this still suffers for large search spaces because we need to try out many different points to find the optimal configuration. And both of these strategies, both grid search and random search, are inefficient and not practical for large models with expensive training time. But despite their inefficiencies, people still commonly use these approaches because they're easy to implement. So another approach to hyperparameter optimization to improve on grid and random search is Bayesian optimization. Right, so with Bayesian optimization, we actually fit a Gaussian model that tries to predict the objective function given the hyperparameters. So we run a set of training runs that are randomly initialized with hyperparameters at the beginning. And over time, our Gaussian model continues to improve based on historical data. And we use this model to inform future hyperparameters for subsequent runs. So the Bayesian optimization is more optimal than random search because we use prior information. And as you can see in this plot, if you look at the red line compared to the black line, over time, we see that we can reach better and more optimal hyperparameter configurations because our Gaussian model is continuously improving based on historical data, which is not the case with random search. However, with Bayesian optimization, we still have the problem that it actually starts off similar to random search. And as you can see with this plot, there's not much distinction between the red line and the black line at the very beginning. So to mitigate this, we can actually combine Bayesian optimization with an early stopping algorithm like asynchronous hyperband, or more commonly known as ASHA. So these early stopping algorithms simply just stop bad performing trials early. So we don't waste time and resources on training hyperparameter configurations that are not very fruitful. So combining Bayesian optimization with these early stopping algorithms like hyperband, we can outperform other hyperparameter optimization models. So with Bayesian optimization hyperband, we use historical data to inform future hyperparameters through our Gaussian model, and we can also stop early trials. But the problem with that approach is that even though our hyperparameter configurations continuously get better over time, subsequent training runs still have to start training from scratch. What if there's a way to tune the hyperparameters without needing to completely restart training? We can do so with population-based training, a hyperparameter strategy created by DeepMind that employs an evolutionary algorithm. So just like Bayesian optimization, we start evaluating a population in parallel of random hyperparameter configs. So in this example, we have 4 different trials that we try out as the initial population, each with a different learning rate. But after some interval, uh, we can stop bad performing trials and actually copy over the progress of good performing trials. So here we see that a learning rate of 0.4 is not performing well. So we stop that. And we can actually copy the model weights from the best performing trial, which is a learning rate of 0.1. And then we can perturb the hyperparameter slightly. So we perturb it from 0.1 to 0.15. So what this allows us to do is focus specifically on the points in the hyperparameter search space, which are providing good results. And we don't have to start training from scratch because we can copy over the network weights from a good performing trial into a bad performing trial. So population-based training is both easily parallelizable and can actually search over dynamic schedules. So certain optimal hyperparameter configurations are not static, but can actually change over time. So population-based training allows us to find these dynamic schedules consisting of training run where hyperparameters are changing during the training process. So yeah, here we see another diagram provided by DeepMind, just comparing parallel random and grid search against population-based training. And yeah, so we see here that for random and grid search, we don't use previous information to inform future hyperparameters. And unlike in population-based training, where we can copy over the best performing trials and perturb the hyperparameters slightly to focus on the most optimal points in the search space. So does population-based training actually work? Well, DeepMind ran this technique over multiple published algorithms, and we see that from many different applications like reinforcement learning to natural language processing, we see that population-based training was able to provide a non-trivial performance improvement over state of the art. So how cost-effective is population-based training? So here we can see a comparison of various hyperparameter optimization strategies on a BERT transformer model. And we see that population-based training has the best accuracy without much extra cost. So even though Bayesian optimization with early stopping provides the accuracy improvement, it is not cost effective because we still have to run initial random samples to train the Gaussian model, and subsequent training runs have to start from scratch. So population-based training can provide the same accuracy improvements or even slightly better accuracy improvements over Bayesian optimization plus early stopping, but also be cost effective because training runs can continue from where previous good trials have left off. All right, cool. So now we've established that population-based training is an efficient method for hyperparameter optimization, but how do we actually add it to our application? So this is where RayTune comes in, which is a library for scalable hyperparameter tuning and provides an easy to use API for running distributed hyperparameter optimization experiments. So RayTune offers a variety of cutting edge algorithms that we've talked about, Bayesian optimization and early stopping schedulers, as well as population-based training. And similar to other hyperparameter tuning solutions, it also works with any machine learning framework that is commonly used today. So Tune is one of the only libraries to actually offer a distributed implementation of population-based training. So, but there's 2 features that really make RayTune special. So the first is that focus on simplifying execution. So with RayTune, you have the ability to launch a distributed multi-GPU hyperparameter sweep in less than 10 lines of code. And in addition, due to RayTune's automatic fault tolerance, you can easily leverage cheap preemptible instances in the cloud. Also, RayTune interoperates with many other hyperparameter optimization libraries. So if you've already tied to one of these other libraries that exist out there today that provide algorithmic improvements, RayTune can actually sit underneath the hood of these libraries and can easily distribute them on a multi-node cloud cluster. So you can take advantage of the algorithmic advancements of these other hyperparameter optimization libraries, but use RayTune for the scalability portion. And finally, we all know that tuning and training is actually just a small part of the machine learning lifecycle. So RayTune provides seamless one-line integrations with experiment management frameworks like TensorBoard or weights and biases, so you can manage your experiments and hand off your model to other tools down the pipeline. So let's go over a quick overview of the RayTune API to understand the flexibility and simplicity that Tune provides. So we start off with a simple model training function. So this is just a simple function which creates a convnet and trains it for a certain number of steps. And our function takes in a config argument, which provides the hyperparameters for a convolutional network. So the first change we have to make is that we simply add a line to report our loss or whatever metric we want to optimize over to Tune. And Tune will then use this metric for its search algorithms or for an early stopping schedule, for example. So in this case, at every step, we do one step of training and then report the loss to Tune. And then all we have to do is just call tune.run. So we just pass our function to tune.run, specify some hyperparameters that we want for our model. So in this case, a learning rate of 0.1. And that's it. Tune can easily now run our hyperparameter tuning experiment and can also easily scale to a large cluster. So you can specify a search space. So instead of a static hyperparameter of learning rate of 0.1, we can do a uniform search across different from 0.001 to 0.1. And then we can also run 100 samples. So this will sample 100 different points from the search space that we defined, and Tune will automatically parallelize the evaluation of these training jobs up to the number of cores in your cluster. So without any changes, we can parallelize this code to our laptop and also to a multi-node cluster. And through this very narrow API, Tune exposes a variety of features, including automatic checkpointing and specifying tuning algorithms. So we can simply add our ASHA scheduler, which we talked about before. So Tune will automatically stop bad performing trials early. And just like that, we can also add population-based training to our Tune run. So we swap out the ASHA scheduler with population-based training. And the only other change we have to make to our code is that we now have to add logic for checkpointing our model. So we take in an additional argument, checkpoint directory. And if it's not none, we can just load that checkpoint into our model. And then every step of training, we save our model's current state into that directory. And the checkpointing here is necessary because, as we saw before, population-based training has to involves moving the state from one training run to another training run. So we need to make sure we save the state into a checkpoint so that population-based training can work accordingly. Great, so now we've talked about how we can easily use Tune to add population-based training to our application. And also how Tune automatically scales our experiment by running multiple parallel trials from anything on your laptop to a large multi-node cluster. So now let's go over some of the new developments with population-based training that we've added to RayTune over the past couple of months. So the first is reproducible traces. So as we talked a little bit before earlier, population-based training is unique because you can actually get a dynamic schedule. What this means is that the optimal hyperparameter configuration is not just specific values, but a schedule where the hyperparameter is changing its value over time during a training run. So with population-based training replay, we can easily reproduce the optimal dynamic schedule that we get from population-based training. So another optimization that we've added is a synchronous execution mode. So this is useful for when we want to run stable experiments with preemptible instances. So with population-based training, usually what happens is that each trial will run in parallel with its own hyperparameter configuration. Then at the point it reaches a certain interval, it will compare its metric against the metrics of the other current trials. And if it's in the bottom percentile, population-based training will carry will copy the state from the best performing trial into the worst performing trial, and then perturb the hyperparameter slightly, and then that trial will continue training. But this could be a problem when the different trials are running in wildly different speeds. So for example, if you consider working with preemptible instances, and let's say one of your current trials crashes because you lose the spot instance, this could lead to unstable experiments because the different trials are no longer running synchronously with each other. So the trial that crashed and restarted is always going to be behind the other trials, and therefore is always going to perform worse because they're never synchronized at the same epoch. So the way we can avoid this is through a synchronous execution mode. So we basically add a synchronous barrier at every perturbation, and we only perturb the trials once all runs have reached the same epoch. So in this example, even though the 0.3 hyperparameter trial crashed, the other trials won't continue executing until that crashed trial restarts and catches up. And then once all the trials are synchronized at the same step, then we can actually perform the perturbation and continue training. So this allows us to run stable experiments with preemptible instances. So lastly, we'll go over a new algorithm that we've added to RayTune called population-based bandits, which is very recently added and is published in Europe's 2020. So while population-based training is very efficient and provides good accuracy benefits over other hyperparameter optimization approaches, it still underperforms for a low population size. And as we see here, for a population size of 10, it's actually underperforming a random search baseline. So the way we can avoid this problem is by combining PBT with Bayesian optimization. And this is an approach that was created by students at Oxford University and is contributed to Tune by an external contributor, Jack, who you can see here, who's a PhD student at Oxford. So he contributed this new algorithm to RayTune, and RayTune is actually the only library that currently has population-based bandits as a search algorithm. So the way that PB2 or population-based bandits works is by combining the best of both population-based training and Bayesian optimization. So recall that for population-based training, when we perturb a trial, we copy over the network weights from a high-performing trial into a low-performing one, and then we slightly modify the hyperparameters and then continue training. But PBT's Achilles heel comes from its reliance on heuristics for exploring the hyperparameter space. And this essentially creates new metaparameters. Now the question becomes, how much do we perturb or mutate the hyperparameter when we're doing this perturbation step? And those metaparameters also needs to be tuned as well. And because of this, it could be the case that PBT underperforms a random baseline with a low population size, since small populations can collapse to a suboptimal mode. So instead, PB2 actually uses a Bayesian optimizer to suggest the new hyperparameters during the perturbation step. So just like with PBT, we copy over the network weights from a high-performing trial into a low-performing trial. But instead of using a heuristic approach to modify the hyperparameters for the new trial, we actually have a Bayesian optimizer, which learns the objective function on all historical data, just like a traditional Bayesian optimizer we talked about earlier, to suggest a new hyperparameter configuration. So the key difference between PB2 and PBT is that population-based bandits can select new hyperparameters from anywhere in the search space, right? So the heuristic-based perturbation approach that population-based training uses means that we start from a good optimal hyperparameter point, but then we incrementally modify it or perturb it over time, which means that it might take a very long time to reach the optimal configuration. While for PB2, because we're using a Bayesian optimizer, instead of just incrementally modifying the hyperparameter, we can actually reach the optimal configuration potentially at a much faster rate. So does PB2 actually work? Well, yeah, it is very effective in resource-constrained settings, specifically for low population sizes. And as you can see here, for a population size of 4, PB2 vastly outperforms population-based training. And even for a population size of 8, while PBT does better, PB2 still performs better or at the same. And here we can see another experiment comparing the two. So this is reinforcement learning bipedal walker. And this is the policy behavior for PPO at 1,000,000 time steps. So here we can see that PB2 has a reward of 270, while PBT has a reward of 220. So PB2 is outperforming population-based training. And this is run with population size of 4. And what PB2 allows us to do is actually search over an extended range for exploration, right? And as we saw earlier, that because we're not doing incremental perturbations, and we're actually using a Bayesian optimizer to suggest perturbations, we can extend our search ranges from to a much larger size, and we can still get to the optimal configuration at a faster rate. So here we can, this is copying over the experiment that we ran earlier, except we're extending the batch size range from 1K to 60K to 5K to 200K. So a much larger range. And we're seeing that PBT does significantly worse here compared to PB2. So how can we use PB2 with Tune? Well, it's very simple. All we do is just replace the scheduler with what was population-based training with PB2, and that's it. No other changes to the code needs to be made. So let's do a recap of what we talked about today. So we went over how population-based training and population-based bandits are two cost-effective approaches for hyperparameter tuning. And they work by continuing training by copying over the state of the network weights from good performing trials to bad performing trials. And specifically, population-based bandits outperforms PBT for a smaller population size because it uses a Bayesian optimizer to suggest perturbations rather than doing incremental updates. And we also saw how we can use RayTune to quickly and easily run distributed tuning experiments and try out all the different algorithms that we talked about today. So what's next? So try out RayTune, some of our PBT and PB2 examples. They're all located on our GitHub repository. And you can also use Ray's cluster launcher to run multi-node experiments in the cloud. And for any follow-up questions, you can look into our discourse, discuss.ray.io, and we'd be happy to help you out with any questions you have. Yeah, so that's all I have for today. So thank you for listening to my talk, and we can go into some Q&A now. Thank you.
Thank you, Amok. That was a very interesting talk. Hey, any questions? Yeah, for people attending, if you have any questions, please post down Q&A. Thank you. So I will ask a question, Amok. So for these different tuning algorithms, can you share some experience of those being used in different production environments in the users that you have talked to?
Yeah, so yeah, it's a good question. Right, so Tune is used not only by researchers, but also in like production environments and for actual those kind of use cases. So one of the, as we talked about in the talk, like hyperparameter tuning is incredibly important for good model performance, and it's very, very useful to make sure that the models that we're training have good accuracy. And we need to make sure that we can tune these hyperparameters efficiently. So RayTune is perfect for, not only for running like small experiments for like hobbyists or for researchers, but also using it as part of like a production environment as well.
Okay, thank you. Any more questions from the attendees? I see one coming up. So for reinforcement learning specifically, what are the sensible default hyperparameters for PBT or PB2? Oh, actually, two questions coming up. I will let you answer, Amok.
Okay, yeah, great. Yeah, so the first question, so for reinforcement learning, what are some sensible default hyperparameters for PBT and PB2? So actually for PB2, one of the main benefits is that there's actually less meta parameters you have to tune. So you only have to provide a bounds for your hyperparameters. and as opposed to like some sort of probabilities for mutations or things like that. And specifically for what bounds to provide for the hyperparameters, that depends on the task that you're trying to train for. Usually how I do it is going through some research papers or some blog posts, seeing what hyperparameters worked out for them, and then sort of doing like an extended range around those optimal hyperparameters and searching over that area. Yeah, so hopefully that answers your question. So yeah, next question, can PBT and PB2 be used with cross-validation? Do you have any examples? Yeah, this is a good question. So currently, Tune does not have built-in cross-validation capabilities, but if you're using another library like scikit-learn optimize, I think that has a cross-validation, and you can use that with Tune. So I'm not sure if so I don't think PBT and PB2 are available in like scikit-learn optimize, for example. So I'm not sure if this is possible currently, but that is a good thing. Yeah, that's definitely a good thing that we should look into, adding like built-in cross-validation support with RayTune. Yeah, so thanks, Roland, for your question. So the next one is RayTune is search and scheduling components. How does PB2 separate search component and scheduling component? Yeah, so that's a good question as well. So PB2 involves both the searching and the scheduling. And then if you're interested in like the technical details, it's only considered to be a scheduler, and you don't use like a separate search algorithm when you're using a PBT or PB2. So it involves scheduling because it not only has to modify like stop, for example, has to stop trials early, or it modifies execution of the trials, but then it's also responsible for suggesting new hyperparameters. So they're both built in together as like a scheduler, but it involves, yeah, like both the scheduling as well as the search component in one library. Okay, so next question is how to work with large data sets since PB2 is not having good performance. What do you consider a large and a small data set? Yeah, this is an interesting question. I think for this one, actually, I'd suggest to reach out to the PB2 authors for more specifics about what are some failure modes about PB2 and where you would where PB2 would shine the most, and like some cases where it wouldn't necessarily work that well. Yeah, I think the main benefit of PB2 is working with small population sizes, but the data set sizes are interesting, and I'm not really I don't have a good answer to your question, unfortunately, but I think the PB2 authors would be happy to help out here. And then yeah, so if you can email Jack, who's the main author on PB2, and he'd be happy to help out by answering your question there. Okay, so the next one is how does PBT/PB2 handle cases where rollout is expensive? Yeah, so that's another good question. I think in cases where rollout is expensive, you probably want to use a smaller population size, in which case like population-based bandits would work the best. So they both work, in regardless how expensive the training is. It's just a matter of sort of trying to have efficient hyperparameter search if your rollout is expensive. So I think in that case, you want to use population-based bandits would be the best for your scenario. Yeah, hopefully that answers your question there. Okay, so next one is in CNN, do you have any benchmarks for the time to converge between PB2 and PBT? Yeah, so if you look at the original population-based bandits paper, which is on arXiv, they mostly do experiments comparing PBT and PB2 for reinforcement learning. So I don't think they actually have any benchmarks for convolutional neural networks or for image processing examples. So it's mostly in reinforcement learning experiments. Yeah, I don't have any more to add to that. I think if you're interested in specifically for CNNs, it's another good question to reach out to Jack, who is the main author for population-based bandits. So, okay, so follow up to a previous question. What are some sensible lower bounds on the number of population samples to use for reinforcement learning? And then when specifying the hyperparameter bounds for PBT, should we take care of the underlying metricness of the space? Example, using a log transform on the bound for a learning rate. Yeah, so these are good questions. So a sensible lower bound. I think if you're using PB2, like 4 trials would be a good lower bound for that. And then PBT, you probably want to raise it to something more, like maybe like 8 to 16 trials. But it really depends for PBT on the initial randomness that's involved in the initial hyperparameter configurations. For if one trial is randomly initialized with a good hyperparameter config that's like near the optimal, then it's you can get to the most optimal configuration with a smaller population size. But for specifically for lower bound, I think 4 is a good number for PB2. And for the second point about should we use a log transform on the bound for learning rate? Yeah, I think it's a good idea. I think working in log space is definitely helps for both for PBT and for PB2 as well. Okay, so does PBT/PB2 now support tune resume? The code base previously suggested that resume functionality may not work for PBT. So I think tune resume should work for both PBT/PB2. Yeah, I'm not sure what version of Ray you were using previously, but I think it should work. And if not, I can follow up again with you. Yeah, Angie, I can follow up again with you regarding this question. So what metric do you usually use for training? Using the last validation loss might be misleading if the model is overtrained. Would be the best validation loss across the epochs. What are your thoughts on this? Yeah, so this is a good question. So like you said, the last validation loss might be misleading. So you could do the best validation loss across all the previous epochs, or an average of the validation loss across the last n epochs, for example. That's another alternative you could use there. So yeah, all of those should work, and using an average might be better in cases where the last validation loss is misleading in case the model is overtrained. Okay, so I think there's one more question. Is there an alternative to syncing experiments during hyperparameter search? Assuming there are no free resources in the cloud, especially when preemptible instances are used, the whole process would be stuck. Right. So I think what this is asking is basically so if yeah, so correct me if I'm wrong here, but I think this is asking for a synchronized execution mode in case one of the trials crashes and you can't restart that, if I'm understanding correctly. The whole process would be stuck. Yeah, and that is true. If one of the trials does crash, and if you're running in synchronized execution mode, and then it can't be restarted again because you can't get a new spot instance, for example, then the experiment would be stuck and you'd have to restart that. Yeah, so that is one drawback of using a synchronized execution mode. But on the flip side, it will result in a more fair experiment since all of the trials will be synchronized at the same time step before a perturbation occurs. So even if they're running at different speeds, you can still make sure that the perturbation, the comparison between the performance of the trials will only occur when they're all at the same time step. So yeah, let me know. Yeah, let me know if that answered your question or not. If I understood your question correctly. Okay, so there's a couple additional questions. First one, defined by search/run. I'm not sure what exactly that's referring to. And for the second question, if the rollout environment changes slightly over time, so each rollout could experience slight out of distribution, does PB2 handle that well? Yeah, that's an interesting question, and unfortunately don't have the answer to that specifically right now. Once again, I think this is a good question to email Jack about. And I've worked with Jack and be happy to answer all of these questions about PB2 specifics as well. And yeah, Jack is the main author on the PB2 paper.
Okay, sounds great. So I have two suggestions. One is for in-depth discussions. We also have a Slack channel. I just pasted the sign up form on the chat. And also on anyscale.com/events, you can subscribe to more events that's coming up. Thank you so much, everyone.
Thank you.
Actually, there are two. Thank you. All right. Thank you. Have a nice one. Great to have you here.